So this first problem I want to look at is really nothing new, but the phrasing is a little different. So just want to kind of help y'all interpret what the problem's talking about. So look at the top. For the following exercises, given that y is some function of u and u is some function of g, so Leibniz notation, find the derivative of y with respect to x using the chain rule. So y is 3u minus 6. And u is 2x squared. Well, then dy dx is dy du, du dx, just like we did in the first video. The derivative of y with respect to u is just 3. It's a line. What's the slope of a line? That m value. Derivative of u with respect to x, it's also a line. The power rule also works on these, by the way. So dy dx is just 6. That's all this problem wants. To kind of connect it with the red method from the videos, you can also look at y is 3 times u minus 6. Y is just, 3u minus 6, and u is 2x. So replace the u with the 2x. So this function is just 6x minus 6. What's f prime? It's 6. The derivative of this new resulting line is 6. That's all that's happening in this chunk of problems. Let me know if you have more questions about them, though. All right, 220. So this is basically asking you to set up the red method that we did. Decompose. Oh, just kidding. It's either the red method or the blue method, it looks like. It just wants you to find the derivative either way. Which one am I doing? 220. Y equals 3x minus 2 to the 6th. And it wants you to write it in y is some function of u and u is some function of g. So yeah, that is the blue method still. U is the inside and y is the outside. The y is u to the 6th and u is that inside function. Then again, the derivative of y with respect to x is just dy du, 6u to the 5th, times du dx, which is 3. And again, this is very similar to what we did before. U is 3x minus 2. This is our derivative. And again, you can check your answer by using the red method. Red method says take the derivative of the outside function and leave the inside alone. And then multiply by the derivative of the inside function, which is 3. That should get you to the same answer. So let y be some function squared. And suppose that f prime of 1 equals 4. And dy dx equals 10 for x equal to 1. Let's look at that last part. Dy dx equals 10 when x equals 1. Another way of writing that. Wait, what? Okay. Dy dx when x equals 1 is equal to 10. That's another way of phrasing this. I was confused, but then I remembered that f and y aren't the same thing. A lot of times we call f and y the same thing. But this is just saying the derivative of f is 4 here. The derivative of y is 10 here. But it's at the same location, right? These are both two ways of saying almost the same thing. All right, like if you wanted to, you could translate this into saying the derivative of f with respect to x, I think. When x equals 1 is 4. Like they both mean the same thing. All right, what else does it want us to do? 238 says find f of 1. Find f of 1. Wait a minute, am I losing my mind? F of 1? All right, well, it's giving us information about the derivative. I have no idea where this problem is going. It's giving us information about the derivative. So if we want to use the information about the derivative, we need an equation for the derivative. I don't know how that's going to connect to f of 1. Oh, maybe I do actually. Oh, this is, so yeah, here's the logic, right? I didn't know why this connected, but I knew it gave us information. So the natural guess is, I don't know why these are related, but let's try to use this information. So the only way to use this information is to take the derivative. And we'll see, maybe it'll help us, maybe not. So if we take the derivative, it will help us. The derivative of y with respect to x, you could also call it y prime. Y prime would be fine. Is equal to, we're going to have to use the chain rule. Derivative of the outside function with the power rule. Leave the inside function alone. Multiply by the derivative of the inside function. All right, that's the chain rule. And now, here's the reason why it's going to work out, is now we know everything here when x is equal to 1. Right, when x is equal to 1, dy dx is 10. When x is equal to 1, I don't know what f of x is, but I know it's the function evaluated at 1. And when x is 1, the derivative is 4 of f. So, that's a funny problem. Yeah, I look through the problems when I'm assigning them, of course. I don't just choose all the odds. As you can see, like especially early on in the quarter, I had like weird selections of problems, but I don't like do them all out. I just like, oh yeah, that looks like it's gonna be a good one. Yeah, this one's kind of funny. It's gonna be 10 equals 8 times f of 1, and it wants us to find what f of 1 equals. So divide both sides by 8. You're gonna get f of 1 equals 5/4. That's kind of funny. All right, 246. Where's my mouse? What are we doing here? Easy information in the table. Ooh, I really like these. Easy information. It's kind of giving things away. I haven't written the quiz yet, but every time I say, ooh, I really like these problems, you should maybe make a note to yourself. Easy information to find h prime of a at the given value. So we're looking for h prime of 0. Looking at 246, where h of x is g of f of x. So we're looking for a derivative. So we're going to have to find what is the derivative. H prime of x is the derivative of the outside function, g prime. Leave the inside function alone and multiply by the derivative of the inside function. This h actually is backwardly named from the ones we usually do. Usually we write f of g. Here we're writing g of f. And specifically, we want h prime of 0. So that'll be g prime evaluated when x is equal to 0. So that's when f of 0 times f prime of 0. And we have to find all these things. We can't evaluate g prime yet, but we can find these two things. And we're going to have to do g prime in another step. So what is f of 0? The function f, the function f I wish I could show my cursor a little bit more clearly. When x is equal to 0, the function is 2. This is why you should never click. As soon as you click, this website just freaks out. Oh my word. All right, we're also looking for f prime of 0. When x is 0, what is the derivative? F prime is 5. Well, now we need to find what is g prime of 2. Well, when x is 2, the derivative of g, x is 2, the derivative of g is negative 1. Our answer should be negative 5. That's how you approach these problems. Just another way of connecting the concepts. All right, I chose this problem last week. I don't remember what 250 is. Hopefully it's a really good one. Oh, it's the same kind. Wait, I didn't choose any of these ones? Did I not assign any? Oh, I certainly assigned some of these. Let's do one of these instead. 250 is basically the same thing. Well, it looks kind of nasty. 256 maybe. I'll do an even one. To help you. You're not assigned the evens, but the formula for the area of a circle is A equals pi r squared. Where r is the radius of the circle. Suppose the circle is expanding, so both A and r are changing. Oh, this is related rates. We talk about this more later. This is a good little introduction. Suppose that r is some function of time. And specifically r, actually I'm going to write it over here. So A is changing, but r is also changing. R is 2 minus 100 over t plus 7 squared. T 2 minus 100 over t plus 7 squared. Where t is time in seconds. And r is in inches. So area is going to be in inches squared. Use the chain rule, dA dt equals dA dr times dr dt. I didn't have to look at this one because I know how the chain rule works. It's just different variables. And remember that we can intuitively kind of think of these canceling, even though they're not fractions and they don't behave like fractions really. Find the rate at which the area is expanding. This is the rate of change. What's dA dt? The derivative of the area function with respect to time. It's how the area function changes over time. This is how the area function changes with an increase in the radius. And this is how the radius changes with respect to time. Okay, tying all these concepts together. Well, once you know what to do, that we really just need dA dt, or A prime of t, finding these individual things is not so bad. What's dA dr? The derivative of A with respect to r. So r is our variable, pi is a constant. Becomes 2 pi r. Because constant multiple rule, pi comes out in front. Derivative of r squared is 2r. Derivative of r with respect to t, let's not do that one in our heads. Let's go off to the side. R is 2 minus 100. I'm rewriting this function. We very frequently rewrite functions with polynomials in the denominator. Write them with negative exponents. It makes it much easier. So then the derivative of a constant is 0. And then we use a constant multiple rule to have this 100. And now we really just need to find what is the derivative with respect to t of t plus 7 to the negative second. It's going to be negative 100. We'll use the power rule. Derivative of the outside function. Bring down the power, subtract the power. Leave the inside function the same and multiply by the derivative of t plus 7. Derivative of t plus 7 is just 1 because t plus 7 is a line. Well, if we simplify that all out, we're going to get positive 200 over t plus 7 cubed. Just doing a quick double check. Yep. So this isn't, we're not done yet though. Remember the problems that we did with Leibniz notation. The last step was always putting everything in terms of the variable that we want. We want to know how is the area changing over time. So our answer shouldn't have the radius in it. The radius is this. So we substitute. It's going to get a little messy. This is 2 pi times the radius, just 2 minus 100 over t plus 7 squared times this other thing that we had from before. 200 over t plus 7 cubed. And now we just clean things up a bit. Let's do that on the next page so we have a little bit more room. This is dA dt, the rate of change of the area over time. First, I want to combine this and this. It's going to be 400 pi over t plus 7 cubed. And then in the next step, we can distribute it to the next thing. I would also take this as an answer. I'm not convinced which one is better. You could also factor a little bit more. There's really a couple of ways of writing this. Actually, there's a lot of ways of writing this. Distributing it is one way. Distributing it would be fine. Putting this all in one fraction is probably what the book would do. But it's not really a big deal. I'll take it. I'll even take it like this. Let's distribute. If we distribute, first one just becomes 800 pi over t plus 7 cubed. Next one becomes 400 times 100, adds 2 more zeros, pi over t plus 7 to the 5th. And then, yeah, if we wanted to combine into a common fraction, this first one would need a t plus 7 squared. And that would give us 800 pi times t plus 7 squared, which we'd have to FOIL out. T squared plus 14t plus 49. Now they have a common denominator, so we can combine their fractions. 40,000 pi for t plus 7 to the 5th. By the way, I just really want to emphasize this is an okay final answer here. But sometimes the book simplifies a little bit further, and that's what I'm kind of showing right here. So again, I want to make sure we have plenty of room, so I'm going to take this to the next page. Distribute out that top, 800 pi times t squared plus, actually I know already what they would do here. Before foiling it out, they would factor out a greatest common factor, which is 800 pi. Factor out the 800 pi from everything. And that leaves us with t squared plus 14t plus 49 minus 5 would give us 4,000, so it has to be 50. All over t plus 7 to the 5th, which is 800 pi times t squared plus 14t minus 1. And then it doesn't factor anymore. So this really is a nicer form of the answer, but it took a lot of simplifying to get here. It should be the same. Should be the same things. Again, if you're ever curious whether you made a simplification error, one of the ways that you can do it, I'll show this off right here and check my answer at the same time. One of the ways that you can do it is actually just graph both functions and see if they're the same thing. So 400 pi over t plus 7 cubed times, oh, it's going to want us to use x's here, times 2 minus 100 over t plus 7 squared. And again, Desmos wants us to use x's. Yeah, one of the ways that we can do this is just graph both of these. Again, we're going to have to change our scale. Let's just go from like negative 10 to 10. And then the y values are probably pretty big. Oh, they're not that big actually. All right, this is the rate of change of the area with respect to time. And then we can graph our simplified version and see if it's the same thing. 800 pi times t squared plus 14t minus 1. All divided by t plus 7 to the 5th. And again, oh, thank goodness. You can see that our simplified version truly is the same function. All right, and that's the rate of change of this area function over time. And again, I'm really kind of going out of left field right now, just trying to illustrate some good practices. Another way of doing this and checking whether this rate of change function makes sense is compare it to the actual area function. The actual area function, I'm just going to replace this blue graph. Oops. The actual area function was pi times the radius squared. And what was the radius? The radius was 2 minus 100 over t plus 7 squared. So the blue graph is the area function, and the white graph is the derivative. So oops, I wanted to go the opposite direction. Let's zoom in. Let's look up until like, I don't know, 3 or something. So notice the relationship between white and blue. Blue is our original function. White is the derivative. So the original function has a minimum right here, has a horizontal tangent line right here, and the white graph has a 0 there. That looks good. Now the blue graph is increasing, so the white is positive. Increasing means positive slope, and it does indeed have a positive slope. And then notice what's happening, what should be happening. The slope is getting smaller here, right? The white graph shows the slope function. The slope should be getting smaller. Is the blue graph? Oh, the blue graph is having a smaller slope, right? It's much steeper over here than it is over here. And it looks like the derivative's kind of going off to 0. Is the slope of the blue graph becoming flat? Yes, it is. All right. So another way to kind of graph your answers and just get some sort of connection and some intuitive, it doesn't prove that your answer is correct, but some intuitive ways of checking your work, okay? And tying a bunch of concepts together, which can be very, very beneficial. So that was a bunch of extra information just to do part A of this problem, but I think it's useful. I don't even know how many people watch these videos. I think I can check. That's the rate at which the area is expanding. Find the rate at which the area is expanding after 4 seconds. Again, we're gonna use this. So after 4 seconds, the rate of change of the area over time after 4 seconds, that's that Leibniz notation again. That means evaluated at t equals 4. It's just what happens when you plug in 4 here. And you can plug that in. Or since we already have the graph, when t equals 4, we can just look. When t equals 4, the area is 4.3, and the rate of change is 1.108. What are our units? Area is in inches squared, and time, I don't remember. Area was in inches squared, and time was in seconds. So it's going to be the rate of change of area over time, so inches squared per second. With every second that passes, at 4 seconds, this is growing. The area is growing by about 1.1 inches squared every second. All right, and the area will change at a different rate at different times. But at 4 seconds, this is how fast the area is increasing. Area is growing at this rate. And notice it's, even though it's a rate, it's not inches per second, because what is it a rate of? Area over time. If we looked at the rate of change of like a volume over time, well, that would be in inches cubed every second, because volume is in inches cubed. All right. So rate is always just what's the units of the top, what's the units of the bottom. All right. And that's pretty much, I think I finished the problem. That's pretty much everything. Let me know if you have any questions. We went way up here again. 256. Where am I? 3.3? How did that happen? I don't know. I'm pretty sure I finished the problem. Have a great day, everyone. And good luck.